Hi, I'm Zor. Welcome to Unizor Education. Today's lecture is called Noether's Theorem and Angular Momentum. Now, the previous lecture was about linear momentum, and this one is about angular momentum. And again, it's all about Noether's theorem. Now, this is the third actually lecture about Noether's theorem. The first one was about energy conservation, and it's related to uniformity of our time, which means physical experiments, physical laws actually are basically the same today and tomorrow, let's say. Now, the second lecture was about linear momentum conservation, and that's about conservation of linear momentum if we are moving along some coordinate forward. And this one is the angular momentum. Now, why so much attention was devoted, like 3 lectures, maybe even more, to Noether's theorem? Well, because it's a foundational theorem which basically, which basically provided the foundation for our conservation laws. They are not just empirical facts that the energy is conserved or momentum is conserved. They are the result of certain symmetries of our time and space. And that's what's very important. So all these conservation laws follow from certain uniformity of our time and space. And it's very important for theoretical physics in general, and in particular to mechanics, to quantum mechanics, to general relativity, to all kinds of theoretical physics. It's very important. I mean, obviously, the conservation laws are very important. Okay. Now, this lecture, as the previous ones, are part of the course called Physics Plus. It's presented on Unizor.com website. I do suggest you to watch this lecture from Unizor.com. You go to this website, you choose Physics Plus course, and among the parts of this course, there is a part called Lagrangian, and that's one of the lectures in this particular part. Okay. Now, why I strongly recommend you to watch this lecture from the Unizor.com, because number one, it's totally free. There is no advertisement, no sign-on or subscription is necessary. You can just go and watch the lectures. And the website contains other courses as well, like mathematics for teens, physics for teens, Math Plus and Physics Plus, relativity. I mean, there are different courses in this website, all totally free. And no advertisement, as I said. Nothing disturbs you from learning. That's very important. Okay. Now let's go back to angular momentum conservation. Now, the previous lecture was not only specifically about linear momentum conservation, it was basically about momentum conservation. What was important is, first of all, we have listed all the prerequisites, and I do list all the prerequisites for this lecture in the notes for this lecture as well on the Unizor.com. You can just read the notes and watch the video presentation at the same time on the same screen. So it's very important. So in the notes I put all the prerequisites, but there is one more prerequisite which we have added in the previous lecture. It's called momentum, and it's basically defined like partial derivative of Lagrangian by the component of the velocity. I will put k here, because if we are talking about system of multiple degrees of freedom, every degree of freedom corresponds to one particular generalized coordinate, so it's from q1 to, let's say, qn. So for any particular coordinate, partial derivative of Lagrangian, which depends on all coordinates and all velocities and optionally time. Partial derivative of this q1 qn, q1 prime qn prime, that's time derivative, and 10 and end time. So this Lagrangian. So if you will do the partial derivative by one particular component of the generalized velocity, that will be a component of the momentum. And well, yes, if this is a spatial, so to speak, like in Cartesian system, our coordinates are spatial coordinates. So if this is a spatial coordinates in, let's say, Cartesian system of coordinates, you will get a linear momentum. And I proved everything about conservation in a general case. And the conservation was, and that's basically the result of the Noether theorem, was if you have independence of Lagrangian or invariance of the Lagrangian of one particular generalized coordinate, which basically means that partial derivative is equal to 0. For example, qk is just absent from the definition of the Lagrangian. Well, then obviously the partial derivative will be 0. So basically this is independence or invariance of Lagrangian of one particular coordinate. Well, obviously there are many practical situations when something goes along one coordinate and nothing happens to another coordinate. If you're going along the x-axis, your y and z-axis are not changing, right? So Lagrangian should not depend on y and z, it depends only on x. So that's an example. So if this is true, then is constant. The corresponding, the same, but partial derivative by velocity component, which is basically a momentum along that particular coordinate, is constant. Now that was proven in the previous lecture. And this is basically the kind of consequence from a more general statement which Noether Theorem actually is all about. Noether Theorem was more like mathematical statement, but physicists just derive from this. If you apply that math to concrete physical entities, you will get this particular theorem. It was proven in the previous lecture. But what's important is that this is not just for Cartesian system it was proven. It was proven for any generalized coordinates. And today I'm going to basically use it as given for one particular type of movement, rotational type of movement. Basically, like a planet goes around the sun, for example. So, what we need right now is the following. First of all, let's define what kind of a mechanical system we are talking about. We are talking about rotation, and for this we need central field. Now that's important. So we are talking about, let's say, planet in the gravitational field of sun, for example. Okay? So it's a central field. What does it mean that this is a central field? Well, first of all, it means that the force is always from sun to a planet, or from planet to a sun. So it's only within this particular radius vector, from the center of the gravitation, or whatever the central field is, maybe it's electrostatic, from the center of the field towards the object which is rotating around it. And we are assuming that in the center there is a source of this force which is standing still. Its coordinate is 0. Okay. Now, the next thing which we assume is that this is a planar movement, which means the planet is rotating around the sun by some orbit, and if you remember from one of the previous parts of this course, Kepler's law, Well, the orbit can be elliptical, can be paraboloidal, can be parabolical, can be hyperbolical. So in any case, it's a flat curve, so everything is going on within one particular plane. And in that plane, we have this planar motion of the planet. Now, what I'm going to do is introduce coordinates, polar coordinates on this plane, r and theta. Now, again, my theorem about momentum conservation was for general coordinates, which means anything. These are as good coordinates as anything else, including Cartesian, for example. And what's important is that I will use that theorem, which I have proven in the previous lecture, the law of conservation of momentum. I will use it in this case, but not for Cartesian, but for polar coordinates. Okay? All right. So let's just basically do it. It's not such a big deal. So what happens is the following. When the planet is rotating around the sun, both r and theta are function of time. So let's think about what I actually mean about angular movement. Well, angular movement means theta goes to theta plus epsilon during some very, very infinitesimal increment of rotation. Something must be conserved in this particular case. But let's see what. What we need is, if you remember, again, dl by dq should be equal to 0. Now, we have only two coordinates. Let's say q1 is r and q2 is theta. So we're talking about, in this particular case, angular increment, and I would like to know if my Lagrangian depends on this. So if Lagrangian is independent of this, if it's invariant to this infinitesimal increment of theta, that means I do have this situation and there is something which is supposed to be conserved. All right, so let's see what Lagrangian is. Lagrangian is T minus U, kinetic minus potential. Okay, now what is kinetic energy? This is just very, very quick introduction to kinetic energy in polar coordinates. Generally speaking, if v is a vector of velocity, then 1/2 of m times magnitude of this vector square, which is basically the linear speed square. That's the kinetic energy by definition. But v we're supposed to actually express in polar coordinates. Now I'll do it using transformation into Cartesian, but there are other ways, a little bit faster. But this is, I think, a little bit more, a kind of obvious thing. Let's convert the this particular polar coordinates into Cartesian. So x and y. X is r cosine theta, and y is r sine theta. All right, from polar coordinates to Cartesian. Now, v is velocity, and I know that velocity vector square is equal to derivative by time derivative of x square plus time derivative of y square. This is kind of obvious thing, just very simple vector algebra. All right, so let's just calculate time derivative of x and y. X time derivatives, it's a product of two functions. So it's derivative of first function times the second, which is r times cosine, r prime times cosine theta, and plus derivative of the second by the first. So first is r, derivative of cosine is minus sine, and derivative of inner function theta, which is theta prime. Now y prime will be very similar. It's derivative of the first one times sine, plus sine is derivative of sine is a cosine, and this. Now, if I will do this square plus this square, now square of this is square of this minus 2 times this plus square of this. In this case, I will have square of this plus product of these two. You see, minus 2 minus 2 product of these, and this 2, so they will cancel out. So I will have only square of this plus square of this plus square of this plus square of this. Now square of this and this, cosine square plus sine square is 1. So square of this is equal to r prime square. Square of this, again, sine square plus cosine square would be equal to 1. So it's plus r square times theta square. So this is my v square. This is my magnitude square of the linear speed of our object. Now, so this is t, and what do we see? We see that t does not actually depend on theta at all. You see, only on theta prime, which is velocity by the second coordinate, the first coordinate, and the first coordinate's derivative by time. Okay, fine. So the kinetic energy is invariant to any modification of angle theta. Doesn't depend on it at all. Okay, how about potential energy? Well, potential energy, as we know, in a central field depends not on the angle, but only on the distance between the sun and the planet, right? It's the Newton's gravitational law. There is no dependency on angle. It doesn't really matter at which angle our planet is towards the sun. It's not dependent. It depends only on the distance. And that's the property of the central field. So U also is independent of theta. So what do we have now? We have the dl by d theta is equal to 0. Because t is independent of theta and u is independent of theta. From which follows dl by dk, by dqk prime is constant. So what is dl by dq prime? Well, again, u is independent of q prime. So the only which is dependent on q prime is this one. So only kinetic energy. So let me write down the kinetic energy again. Kinetic energy is equal to 1/2 m r prime square plus r square theta prime square. So that's my kinetic energy, and that's the only thing which depends on my theta prime. So what's the derivative by theta prime? Well, this is not dependent, so this goes out. Only this remains. So r square is not dependent, so it's like a constant, so it goes outside. Derivative of q prime square by q prime is 2q prime. So 2 and 2 will cancel out, so I will have m r square theta prime. and this is constant. This is the conservation of this particular thing. Now, what is this particular thing? Okay, that's another story. Now, there is such a thing which is called, I will use lowercase l. Usually it's uppercase, but I don't want it to be mixed with Lagrangian. So lowercase, that's m times vector r cross product vector v. And this is vector. So this is called angular momentum. Okay. So what's interesting is, let's just consider again central field, planar motion. So the planet goes, let's say, around the sun. R is between sun and the planet, right? R. Now V is movement within the same plane. Now cross product of two vectors which are in the same plane is perpendicular to the plane, right? So if this is the plane of motion, this is the sun, this is the planet, this is R, and vector V is within the same plane. So their cross product goes up or down depending on, orientation, but it doesn't really matter. It's perpendicular. Now, so that's basically called an angular momentum. Now, what is the magnitude of angular momentum? Well, we can calculate it, and all the calculations are in the notes. Detailed calculations are in the notes for this lecture, so you can just write it down. But in a very, very quick way, I will try to derive it right now. Now, vector r, let's convert everything into Cartesian coordinates. Now, if I will have the x along the r, and the perpendicular would be x, y, and z would be obviously upwards. Now, so x will be within the r, so the three Cartesian coordinates of the vector r would be r, which is the length, 0, 0. Now, along the y, we need the v now. V would be, well, what I will do is, if I will do this type of thing, this is x and perpendicular to x would be y, then we can always represent this vector v as with two projections on x and on y. Now, projection on the r would be obviously speed of the changing of the distance between. Projection to the y would be only angular. Angular is speed would be r times time derivative of the angle, and the z would be 0. So these are three-dimensional Cartesian representation of vectors r and v. Now, if I want to calculate their magnitude of their cross product, if you remember from vector algebra, you can do it this way. You can have a matrix I, j, k. This would be r, 0, 0, and that would be r prime, r times theta prime, 0. And determinant of this matrix would be the magnitude of cross product of this vector. So again, if you don't remember, you either take me for this word or go back to one of the courses which are for vector algebra on the same website, unizor.com. You can always do that, or from any other source. So what is the determinant of this? Well, it's I times determinant of this square, which is 0 because it's two zeros, plus j. I cross j column and j line, and I have r prime 0, 0. Again, determinant is 0. And k, I do only this, which is this times this, minus this times this, which is r squared theta. R squared theta prime. Which is exactly this. So that's why if you will calculate the angular momentum according to the rules of classical mechanics, you will have the magnitude of the vector exactly the same as conserved quantity obtained from this Noether theorem. So as you see, if you have something like a spatial coordinates, like Cartesian coordinates, then invariance of particular coordinate or symmetry of the Lagrangian relative to under this particular translation of this particular coordinate cause the linear momentum conservation. But if this particular coordinates is not Cartesian, but let's say rotational, polar coordinate for rotation in a plane in a central field, then we will have the conservation of the angular momentum in this particular case. Whatever it is, the theorem was exactly the same. It was the theorem generalized coordinates. It's just application of this same theorem to, let's say, Cartesian coordinates gives you linear momentum conservation, and application to polar coordinates, they're all, represented in generalized coordinates. So for the polar, you will have the angular momentum conservation. And that's the beauty of this theorem, because it gives you the different conservation laws based on whatever the system of coordinates you are, and whatever particular coordinate is actually, it's called cyclic, which means the Lagrangian doesn't really depend on it. So if this coordinate is cyclic, then the corresponding momentum would be preserved. Okay, that's it. So I suggest you to read the notes for this same lecture. In some cases it's more detailed than whatever I'm telling right now. And it's always good if you hear about something, if you watch some lecture and then you read exactly the same material, maybe present it in a more verbose way. It's a very, very helpful thing. That's it. Thank you very much and good luck.